the equation was 1 upon r square d by dr
r square
d psi r by dr is equal to chi square psi r, where what is psi r? It's basically electrical potential. At radial distance r. Okay. And in fact, already last time seen value of chi square is equal to what? Is equal to 4 pi epsilon
kt
summation in I0 z I square E0 square
psi r.
Okay.
Sorry.
Not psi r. It's only
Yes.
this much. Is a chi. Well, we're going to see afterwards the interpretation of chi. Okay. This is basically, if you see, if you show this equation to any physical chemist, okay. Now this is a differential equation, and we have to solve the differential equation. Okay. Actually, our ultimate aim is to get psi r as a function of r, radial distance. Is it not?
Yes.
So, it's a typical, you know how physical chemists proceed. We have to use basically a kind of new variable, or we can say trial function. So I can introduce trial function, okay, or new variable. Psi r is equal to mu upon r. Okay, so I'm defining a new variable now, and it's a very logical one for us basically to solve and to assume such variables, because I know that my electrical potential, okay, is when I going away from ion, my electrochemical potential is going to fade up. Obviously, it's fade up, right? So it is going to go down like this. So what I'm assuming here, it is following the function of 1 upon r. Okay, that is my. It is basically wide approximation. I mean, it is just a intuition for physical chemist. You can say. So my psi r is proportional to mu into r. Okay, my psi r is proportional to 1 upon r. This is assumption. Okay, and I get such trial function. Okay, or you can say a new variable. You can call it if you want. This is new variable. Okay, obviously I have to substitute this here in this equation, and what I get in d psi by dr is equal to, I'm going to determine derivative. I need derivative here, right? I need this derivative here. So what I'm going to do, I'm going to evaluate for derivative for this d by dr mu by r. Okay, so what I get, mu d by dr 1 upon r, is it not, plus 1 upon r d mu by dr, you know already. Okay, 11th standard mathematics. So if you evaluate this, okay, what we get is, after jumping 1 or 2 steps, what you get is minus mu r square plus 1 upon r d mu by dr. Okay, what is next? Once I get this, I can substitute this value in this equation. Okay, linearized Poisson-Boltzmann equation. If I do that, what I'm going to get, okay, is 1 upon, after substituting, linearize Poisson Boltzmann equation, what I'm going to get is this 1 upon r square I'm just plugging the values, right? R square d psi r by dr is equal to 1 upon 1 upon r square d by dr. R square, I'm just copying my notes. You just check afterwards. Okay, and if you it's a simple derivative you have to evaluate here, and if you do that, okay, what you get actually is 1 upon r square. What you get is 1 upon this is equal to, what you get is 1 upon r d2 mu by dr square. Okay, you can try at home. Okay, and even if you refer Bokkers and Reddy, it must be given there also. Just try at home this whole derivative. Okay, and if you do that, you get this equation. So what I'm going to get now is that now my this linearized Poisson-Boltzmann equation will become 1 upon r d2, because this is equal to this, right? So I'm going to plug in the value d mu by dr square is equal to chi square mu upon r. Okay, you must have seen I have this. I have just evaluated this part. Okay, so this is nothing but this equation becomes like this, or I can write this as d2 mu by dr square is equal to 1 upon r d mu by dr square is equal to chi square mu r, or rr will go, and what I get is, I'm writing, I think I wrote 2 times, d mu d2 mu by dr square is equal to chi square mu. Okay, eventually forms this after doing all this jugglery. Okay, this what we are having, this linearized Poisson-Boltzmann equation, okay, has this form now in terms of mu. Now already you have seen such equation, right? Before also you have solved such differential equation. You have solved such differential equation while solving this particle in a box problem, is it not? Also you have used this equation in solving the radial part of hydrogen atom.
Yes.
Okay, and also you have solved use this equation in this simple harmonic motion, is it not? So solution of this equation already known to you, right? Okay, solution of such differential equation basically is mu is equal to a e raised to minus chi r plus b e raised to plus chi r, is it not?
Yes.
Solution for this equation, generalized solution for this equation is this. Already you actually derived all this thing in your first year M.Sc days. Okay, so my now thus if I put it into my psi r is equal to mu by r is equal to a by r e raised to minus chi r plus p by r, okay, e raised to plus chi r. This is my psi r. Okay, it's very pretty simple actually. What we have done is already we have did before also. Okay, so we'll go ahead with this now. This is generalized equation. Now, what should be the next step now? Can you tell me what is an instinct? Physical chemist instinct. What should I do next? Can you hear me?
Yes.
Yes. What is the next step?
Taking log.
No. Next step basically in this whole equation is A and B both are arbitrarily chosen constant, right? Okay. So we have to evaluate value of A and B. Is it not?
Yes.
Because that was arbitrarily chosen. Okay, in the process. Okay. So now we have to use some mathematical, will give you very generalized solution. But now as a physical chemist, we have to think about the equation. Already I know that my psi r is fading up with distance. It is decreasing with the distance. Is it not?
Yes.
So obviously in situation like that, okay, if that is so, then my best representation of psi r is going to be this. Okay. If B is finite, my potential will increase with R, but that is not truth. Truth is my function is decreasing with basically distance. So obviously for that I have to assume as already we know that when R tends to infinity, my psi R should tends to 0. Is it not? Because what I have physical picture of this, what I understood is that psi r versus r, it is fading up with distance, right? Well, so if this is true, then obviously my at that condition B has to be equal to 0. So my equation will become psi r is equal to A upon r e raised to minus chi r. Agree? Now the next step now, the last part. Now we have to evaluate what is A. Okay, we must know what is A. So how do now tell me again what is an instinct tell us? What is instinct tell us? To evaluate such constant, what normally we do, we use basically a boundary conditions. Remember this?
Integration.
It is basically boundary condition. We have to see what will happen to function at extremes. Okay, and in our case, extreme is going to be we are going to use very hypothetical super dilute solution. Okay, suppose if you use hypothetical condition, it's a boundary condition. Okay, where my solution is very dilute. If I assume that my solution is very dilute, then obviously the interparticle separation, the separation between two ions is going to be very large compared to the ionic radii of the ion. I repeat, if I use very dilute solution, then my ions are going to be far apart from each other, such that my ionic radii will become negligible compared to my distance between the ions. Agree?
Yes.
If that is so, that means I am trying to use now, okay, point charge approximation. So I am assuming my ions is just a point source, okay, point charge. It doesn't have, because its radius is negligible compared to interparticle distance. Okay, if that is so, then I am using now so-called point charge approximation. Exactly the same way from the distance, in the distance, even if you have got light source in closed loop, you may distinguish it is basically a normal incandescent lamp, or you can distinguish between maybe candle, or it distinguish basically it's a LED light, but from closed loop. But if you go 1 kilometer away from that source, you will see only point source, right? You can't distinguish whether it's candle, whether it's an LED lamp, or it is an incandescent lamp. You can't distinguish. That is a point source for you. Is it not? Exactly same way. Large distance. If that is so, then the potential around that ion, okay, potential around, initially when it was not dilute solution, the potential around that ion is due to two factors. One is that ion itself, okay, and because of the ions present around that ions, okay, the electric field around that ion, okay, because of two things. One is, by ion has got charge, right? Because it will generate its own electric field, and also around that ion there are many ions opposite the charge. Ionic cloud is there, is it not? So that will also generate some electrical field. So the electric field around the ion, okay, is due to two factors in normal situation, because ion itself and because of ion present around that ion, that is cloud. Okay, but now in my super dilute solution, my cloud is so diffuse and long. Okay, in that situation, what will happen? In that situation, the the electric field around the reference ion is that ion itself. Okay, and which is nothing but equal to, so electric field, I will write super dilute solution in solution. The electric field around reference ion is due to ion itself. Okay, which is nothing but psi r is equal to zi e0 upon epsilon. This we have already seen. Okay, so this one thing will happen in super dilute solution. My electric field or my electrical potential around the ion is due to ion itself. Cloud will not impact on this because cloud is so far apart, is so super diluted, ions are so away from each other, so you don't see really the interaction. Okay, one more thing will happen at that dilute condition. In dilute condition, in dilute solution, my charge density in the bulk in I0 is also is going to be 0, tends to 0. Okay, obviously my ions are solutions dilute, so my ions are also away from each other, so it will be going to be basically 0. Ni nothing but a charge density. Actually, if you go back and see your notes, it's charge density, number of ions per volume, unit volume. So that is 0. Then what will happen? My chi square is equal to 4 pi epsilon kt summation n I0 square 0 square. Okay, if my n tends to 0, what will happen to chi? If this tends to 0, so obviously my chi square will tends to 0. So in dilute solution, okay, my chi square is going to be tends to 0 and psi r is equal to, okay, these two things will happen in my dilute solution. Okay, well, my chi square is equal to tends to 0. Obviously my chi tends to 0. Okay, so e raised to minus chi r will tends to 1. Agree? So at that limit, so limit, sorry, so limit ni0 tends to 0, my psi r is going to be a upon r. Agree? Because rest after this equation e raised to minus, right? Go back and see. See, our equation was, my equation was this. Okay, since my this tends to 0, this tends to 1, so my psi r is going to be a by r. Okay, so my psi r, okay, limit psi r is equal to a by r. So if you equate this with our original equation, then that means a by r is equal to zi e0 upon epsilon r. So therefore my a is equal to zi e0 upon epsilon. So put the value of this in psi r is going to be, I'm putting value of a now, zi e0 upon epsilon e raised to minus chi r upon r. This is how my potential will change with distance. Okay, in my ionic cloud. Okay, did you understand this part? It is very simple, pretty simple. Okay, so this is one part. Now second part, once I understood psi r, okay, I try to understand what is going to be my excess charge density now. Okay, that is rho. Again, I'll come back to my linearized Poisson equation. Okay, sorry, I will come back to Poisson equation of linearized. Poisson equation is 1 upon r square d by dr r square d psi r by dr is equal to minus 4 pi upon epsilon rho r. So I am trying to now correlate psi r with rho r. Okay, and my linearized Poisson-Boltzmann equation okay, I have 1 upon r square d by dr r square d by r by dr is equal to chi square psi r. So if I equate these two equations, because my left hand side is equal, okay, my left hand side is equal, so equate these two equations, what I will get is minus 4 pi upon epsilon rho r is equal to chi psi r. Okay, or if I rearrange this, or my rho r is equal to minus epsilon 4 pi chi square psi r. If you put the value of psi r, already you are derived, right? Is it not? So what I get, rho r is equal to epsilon 4 pi chi square, the value of now psi I e0 upon epsilon e raised to minus chi r upon r. Is it not? Option go, and what I'm going to get is minus zi e0 upon 4 pi chi square e raised to minus chi r upon r. See, this is my equation for rho r. Okay, what it tells us basically. Okay, what if you see this equation basically rho r. Okay, in fact, if I try to plot this equation, excess charge density around my reference ion. Okay, what I'm having basically, what I say, this is my reference ion, and there's a density around that reference ion, right, of oppositely charged ions. Okay, so excess charge density in that cloud, okay, would vary with radial distance, or how, with this fashion. Okay, it's obvious, no? Near the ions, there will be more, the cloud will be more denser. Away from ions, cloud will be less denser. Is it not? Well, but interesting part is over here. What we have seen in atomic model. So you'll more appreciate that part. This is basically changing rho with r. Okay, but imagine now, if you suppose I have to determine now how the number of charges or charge density means what. So this is my positively charged reference ion, and there is a cloud. Okay, so what I'm interested basically in, how many charges are there in the chosen shell. Okay, I can choose a shell in the cloud, okay, of thickness dr at distance r. So I have chosen the shell of thickness dr and distance r. So what I want to know now, what is the number of charges in the chosen basically in the chosen ring or shell. Okay, so if I do that, which is nothing but equal dq in that particular shell, number of charges in that particular shell, in shell of thickness dq dr, sorry, okay, at distance r. Okay, so my dq is equal to obviously charge density at distance r into thickness of shell, which is 4 pi r square dr. So this is excess charge density, and this is what basically volume of a shell. Okay, 4 pi r square into dr is a volume of the shell, is it not? Okay, so volume of the shell into density will give you number of charge in that particular shell. Okay, so what if I substitute the value of this rho r, what I get is basically dq is equal to minus zi e0 upon 4 pi chi square e raised to minus chi r upon r into, this is rho, okay, into 4 pi r square dr volume. Okay. Okay. So, which if I simplify it, okay, sorry. What I get, okay, is dq is equal to minus zi e0 chi square r e raised to minus chi r dr. Okay, so I can write a little bit different fashion. So dq is equal to minus zi e0 e raised to minus chi r I square r dr. See, if you look at this equation, okay, you'll immediately realize that my number of charge in that particular shell of volume this 4 pi r square dr, okay, how it is changing with the distance r. See, now there are two functions here. One function is basically this, okay. What this function is doing? This function basically, this function, okay, is trying to decrease the number. Okay, it's decay, exponential, right? It's going to decay, and this function will try to increase linearly with the distance. This function, this part of the function will try to decrease the dq with distance r, and this function, this part of the function will try to increase dq with r. So that tug of war between two functions. Okay, so what will happen then if you try to plot it? How does it look? If you try to plot it, okay, I'm plotting r versus dq, okay, at distance r. Okay, how does it look? Okay, it will increase initially because the linear function is there, right? This linear function is there, so it will have to increase linearly with r, and at higher value this function will dominate. Okay, and what will happen at higher value of r? It will start decaying with distance. Did you remember this plot in atomic theory, in quantum mechanics?
Yes.
This is there we call radial distribution function. Remember this?
Yes.
Huh? This radial distribution function. Okay, and this, what this distance? This is where exactly we mark what is atomic radii. Remember this? Is it not? In case of hydrogen atom, you try to see exactly where we mark. Here also, in fact, this theory is developed before proposing hydrogen atom, structure of hydrogen atom. So many ideas basically in atomic theory are borrowed from this particular equation. Here also, in ionic cloud, there is central reference ion, positive ion, and around it there is a distribution of various ion charges. Okay, the dq, number of charges in the shell, the maximum. Okay, at this point. Okay, actually, in fact, you can take derivative of this equation with respect to r, and then equate that derivative, okay, to 0. You can work it out at home basically. Okay, and in fact, you'll find that if you do that at that maxima, that is dq by dr is equal to 0, you find that this r distance at that maxima, okay, is nothing but equal to, find this r max. You can see if you want, right? R max in fact is equal to 1 upon chi. And you have to work it out at home basically and see if you try to do that. If you take derivative of this, okay, and then mark dq by dr is equal to 0, you'll find that at that point, at a maxima, you'll find that this r maxima is equal to 1 upon x. Okay, and in fact, that means what? What is the interpretation of chi is called, in fact, is called Debye Huckel reciprocal length. Chi is called Debye Huckel reciprocal length. Where exactly that is interpretation of chi. Okay. See, the physical significance of chi. What is chi? Chi is basically Debye Huckel reciprocal length, where maximum numbers of charges are there in a particular shell, like atomic model. Okay. Exactly the same we have got reciprocal length. Okay. There we have got atomic radius, you have got reciprocal length. Okay. So what I propose you now,